Good afternoon. Thank you for forfeiting your lovely afternoon outside in the sunshine in Cambridge. I know how rare that is to come and spend some time with me. My name is Aga. For obvious reasons, everybody in Cambridge knows me as Aga. My full name is Aga Iwasiewicz-Wabnig, but it's spelled here in case if you want to find me on LinkedIn later. And this talk is exploring a little bit about, can blue skies research solve real life problems? So I thought I will give you a range of possible examples because I wasn't quite sure who's coming, so I don't want to focus on one particular one and lose you on it, and then some other people will be bored to death. So blue skies research, well, to my definition, blue skies research is basically discovery research, something that is driven by curiosity and people who are just really willing to push the boundaries of knowledge that we currently have. So I thought, where do I start? So the first example is something which I thought was as blue sky research that was already beyond the atmosphere, and it's actually black sky. So these are some pictures of galaxies. And I think this is a good point to start, because if you think about the real societal impact, this is probably as far as you could start. Do you know of any applications of astrophysics that you could quote to me? I'm not going to pick on you right now, but can you think of anything that astrophysics has delivered for the society? Yeah?
Common filter and a GPS.
Yeah?
What? What did you say, sir?
The common filters and the GPS.
Oh, it's sort of, whichever way around. The examples I'm going to talk about are slightly different, so thank you for not picking one of mine. But let me tell you what is going on in this particular scenario. There are galaxies. And we've developed technologies that give us possibility to scan the sky and generate humongous amounts of data. Too much data, in fact, for any researcher to really want to spend their time and classify every single new galaxy that we found. So they're using Bayesian analysis algorithms that are used to looking at something and telling apart something that was perceived as normal and usual from something that is abnormal and different. So if Bayesian analysis looked at something like this, it will say, oh, okay, this one we know what, this is category A, whatever, this is category B, category C. That one looks a bit odd. I'm not quite sure. Maybe I'm going to call the scientist. So that's sort of the typical use of Bayesian analysis in astrophysics, actually quite a long time ago already. And that led in a series of serendipitous conversations to two particular applications. One of them is looking at a set of data that we do know what it is very well. We know that letters look like A, B, C, D, and so on. We know what letters can appear and numbers on the license plates. So what you get is a methodology to read blurry license plates from speed cameras. So don't speed because we know how to find you. And the other one is looking at the mammograms, and it provides you an opportunity to find amongst the picture some of the cells that don't look quite normal. So the algorithm can say, this is all as expected, that other part is not, please call the doctor. One example. Another example that has a little bit more connection to Maxwell Centre is Cambridge Display Technology. It has started way before Maxwell Centre was even conceived of. But there were 3 researchers working in the Cavendish laboratory on the polymers that emitted light under specific conditions. And in 1989, a first working organic light emitting diode appeared. It sounds glamorous, but it's basically a little dim light coming out from a small sample under the microscope. What happened very quickly in succession is they realized this could have a potential application. Now, this is way before Cambridge had Cambridge Enterprise Technology Transfer Office. Nobody quite knew how to go about commercialization of research. But they've actually got to patenting first working displays, and a year later, company, Cambridge Display Technologies, were funded. So, long story short, very quickly, still, a lot of other technologies emerged around it. And they've demonstrated at that point, cutting edge, 56-inch organic LED displays. Why am I talking about it, you might wonder? Well, first of all, Richard Friend, one of those researchers, is the founding director of the Maxwell Centre. And I would claim this exposure to potential applications of blue sky research is one of the reasons why we thought we need a Maxwell Centre. The other one, Jeremy Burrows over here, has stayed with the company. He and his team are currently also based in the Maxwell Centre and working with us on any new technologies that the material science can underpin. And then finally, since we're talking about impact, those things are now taken for granted. They sit in your pockets, they are hanging on your walls. That is impact. And actually, if you think about it, it's fairly quick to the scale where those things are completely ubiquitous at the moment. So when I go and talk to companies, I usually start with this. Consider working with us because we think slightly differently. And from that difference, impact can follow. So you're probably sitting here and thinking, well, university research is quite important, but it's also very costly. So what about this? How much this university contributes to the UK economy? And I'm going to ask you to think of a number in your head. Make it easy, any given year. Do you have the number? Shall I proceed? Okay. It's that. It has been estimated last year that we contribute about £30 billion annually to the UK economy, this one university. And if you dig deeper, it actually is mainly coming from spin-outs, companies, and associated partnerships. Now, what it means, first of all, to put it in bigger picture, what is 30 billion? It's such a big number. Well, it's about as much as 4 Premier Leagues if we had 4 of them. We just have 1. Now, it's, I think, a good return on investment. Every pound spent into the university delivers almost 12 back to the society. But that's just money. So let's move on to something else.
Sorry. Just one. Could you break that 30 billion down at all? Do you have any?
I can, if you want to go to that link over there. Then the full research is explained and is substantiated what it means and where it comes from exactly. So it's linked on the university website as well, but I can maybe find you later. Right, so in this room, I hardly have to tell people why Cambridge is special. Well, it is an excellent university of a great history, a lot of really excellent scientists, but we also sit in the middle of one of the most leading innovation clusters in the world. What I would argue personally is that's the baseline, and where we are going on forward is based on a particular way we work in partnership with external parties through knowledge exchange and innovation. So within all of this, the role the Maxwell Centre plays is being an anchor, a place where industry and academia can come together and work on really important societal issues. Now, our focus primarily, as you would not be hopefully surprised, veers to some of the biggest problems of our times: sustainability, healthcare. And we do that by putting together companies and researchers from many different institutes and departments, all under the same roof, and we give them the same coffee. That's very secret sauce. Now, I will put this here in case if you're interested in the detail. What I'm trying to say about the Maxwell Centre is think of us as a gateway to the university. This is a mechanism where people and ideas can flow in and out freely. It has represented a substantial investment, both from the government but also from our industrial partner from the very, very end, from 2013. At any given time, we have several companies in the building. We work across pretty much every department in physical sciences and technology and also going beyond. And we are very well connected. We have developed mechanisms how our alumni and people who come and work with us can take an idea into commercial reality, quite successfully actually. So one number I'm going to point out to is, this is already outdated because we do not bother them with questions every year. We've asked 2 years ago. Since 2017, the alumni venture of our entrepreneurship program that we run, and I'll tell you a bit more about, have raised over 130 million pounds and still going. So you'll think, okay, so there is a lot of data. How does it all come together? And to me, when I look at the possibility of any new potential partnership of collaboration, I consider this. The University of Cambridge, as you may already know, has a vision statement, mission statement that starts with, the university exists to contribute to society. That is the societal impact, that it's the core of what we try to hopefully achieve together. But of course, if you work with companies, you cannot be naive. Companies need to achieve return on investment. They need to look at the commercial opportunity in any particular project or idea. So we have to take that into consideration as well. And it's actually really good because you bring two perspectives together. The second secret sauce that I would put in here, however, that's not enough. You not need to only have an overlap of interest, but if your collaboration is able to make both places better or multiple places better through some knowledge, capability, skills development, that's the sort of hotspot that we would like to aim for just here in the middle. I don't know how much you know about history of Cambridge, but one fun fact is Venn diagrams also come from our university. So here we go, big tick. Now, so where do we take it all? I had the privilege of taking over as the director of the Maxwell Centre just under a year ago, and it gave me some time to think about what is going to be our strategy, where can we go there? And this is what I ended up with. I think we can focus on the science and technology that is to be enabling the robust and healthy, resilient society of 2051.
Why 51?
Ah, thank you. We have a lot of deadlines ahead of us. There's quite a lot of decarbonization targets that finish at about 2050. Now, is anybody thinking what happens on the day after? And it sort of reminds me of this, that's why there is a piece of a wedding dress on this slide. It reminds me of the wedding day scenario. You've set the date, you've spent a lot of money on your clothes, on the dress, on the suit, whatever it might be, and you know you need to fit in those by the specific deadline. So any grueling diet, any potential exercise regime that's completely unsustainable in the longer term, all is on the table. But the problem is, the day after, you haven't quite thought about the marriage, you only thought about your wedding day. And it's really quite likely that a few months later you will no longer fit into this wedding dress. So that's the scenario we really cannot afford at the moment of our society. So if I unpick it a little bit in a little bit more detail so you can get a feeling about what motivates us at the Maxwell Centre, it would be this. The usual problem comes from products, from material things that the society produces and consumes. So if we were to aim as a target for zero waste, that nothing we do affords any level of waste generated, then we can actually look at improving energy efficiency, all the way from designing any new electronic device that we're currently having in our labs, all the way to this systems thinking about energy systems. Next things comes, besides energy, is the materials, the things we take out of the ground in order to produce our phones, or cars, whatever it may be. Can we actually optimize what comes out the other end as waste and recover some of this value? Can we use them somewhere else? How do we make things also matters. Where our supply chains are situated, which way our materials have to travel before they really hit the store you go and pick them up from. And can we think about proper circularity? We tend to think about circularity as a sort of version 101. You have your plastic bottle, you use the water from it, you put the bottle in the bin, then you recycle it, and another plastic bottle appears. There is so much more we can do. You don't have to think about it. Maybe one person's or one company's trash can is somebody else's gold mine. That's the direction of travel we should be going for. That's fairly complex maybe, but the health tech side I hope is very self-explanatory. If we are thinking about ideal society 2051, we want to have access to technologies that support us not only in illness but also in health. And we have all new technologies such as wearable devices that we can, for example, start capitalizing on a little bit more. And that includes, of course, not only the physical health, but the mental health, because that's one thing I have a feeling that the pandemic will leave quite a mess for us to clean up. But again, thinking about 2051, I cannot imagine a future where it's not underpinned by data, and that data has to be free of bias, it has to be representative, and we have to be able to make some decisions based on it. So this is the picture of where we have with the research going ahead. We're not quite there yet, of course, we just started this year. How do we go about it? So Maxwell Centre itself, we're not able to be there today, unfortunately, but what we have done, we've hopefully engineered a place where serendipity and strategy can coexist in research partnerships. What that means is that you have all of those conversations that you knew you wanted to have, but you can also come in, grab a cup of coffee, and magic can happen. You can meet somebody you didn't plan to meet, you can have a conversation you didn't plan to have. It all starts in research partnerships being interdisciplinary and cross-cutting across the disciplines. So you will not be surprised that our main focus is on School of Physical Sciences, Technology, and for the health tech, of course, medicine. Now, we also started innovating around how we bring people together, how something that is just about ready to exit from the research lab into something next can be taken forward. So, having a very nice building, what we can do is we can convert a couple of spaces to be our demonstrator labs. And that's what we've done. And so far, there is a range of projects that we've gone through. I will show you two of those. I will show you one of the first ones and the current one we're working at the moment. What it means is that it's not a typical lab in the sense that we've put every single plug we could think of, every single outlet, every single gas line, which means projects can come and go very quickly and you can adapt to those conditions. This picture is not a very typical picture of a research lab as well, because you can see hundreds of samples going in front of the person. Usually you do one or two, maybe if you confirm that your thesis is correct and move on. In here, we want to demonstrate that the technology can be scalable, and that means taking it from a square centimeter to square meter, and then handing it over to somebody who can make more. Okay, this is going to be one of the tricky things that I hope in 2051 we no longer have a problem with. Let's see if my video plays. So, since I said we cannot go into the Maxwell Centre as of today, I thought I'll show you a video that presents this project, and it also shows you how our labs look like from the inside. So please enjoy.
My name is Erwin Reisner. I'm Professor of Energy and Sustainability in the Yusuf Hamid Department of Chemistry. I look after the chemical and catalysis aspects, and in my team is Dr. Virgil Andre, a research fellow at St. John's College, and Dr. Motia Rahaman, also a research associate at St. John's College and a Marie Curie fellow in the Department of Chemistry. We develop technologies to convert solar energy into renewable fuels. Specifically, we build solar panels that can harvest sunlight to produce renewable fuels such as hydrogen and carbon feedstocks. What we try to develop is really taking solar panels and coat them with catalytic layers so that we can make renewable fuels instead of electricity. What we are aiming for is a real-world demonstration where we can take our technologies from the laboratory into the real world and demonstrate that this chemistry, the conversion of solar energy directly into renewable fuels, is feasible.
I'm Sam Stranks. I'm a professor of optoelectronics in the Department of Chemical Engineering and Biotechnology here in Cambridge. We lead the aspects on the halide perovskites, making scalable photoabsorbers. We've used facilities right across the university. We've used facilities in chemistry for the photocatalysts. We've used facilities in the Department of Chemical Engineering and Biotechnology for some of the depositions. And we've also used facilities in the Maxwell Centre in physics, where we've been using the Henry Royce Institute ambient cluster to scale up these halide perovskite materials to make the solar leaves. So we've been working together for the last 3 or 4 years. We've been working from small lab scale demonstrations, and now we've recently hit a milestone of having a meter square panel that we've been able to test outside.
The first crucial step to fabricate our solar device is to make sure that the substrate is as clean as possible. In order to do so, we have a protocol to remove any kind of organic material and dust from its surface. Once we have thoroughly cleaned the substrate, we proceed to evaporate our host selective layer, which is key to ensure that the device works as it is supposed to. This layer has to be uniform, homogeneous, and free of pinholes, to facilitate the further deposition of the perovskite absorber and the electron selective layers. The deposition of a high-quality, large-scale perovskite layer is essential for the success of our artificial leaf prototype. For this, we use the hybrid module of the Royce Ambient Cluster tool, where we have access to a vacuum deposition chamber where we can co-evaporate 4 different sources to obtain a complex perovskite alloy. This perovskite efficiently absorbs light and produces charge current, but also is very stable over time, which is very important for our purpose. After the deposition of the perovskite, we evaporate the electron selective layer and the metal contacts to close the full device.
Until now, we have seen how the light absorber is deposited, but for the purpose of our project, we also need to have a catalyst, a material that will be able to convert small molecules like water or carbon dioxide into a useful product, syngas, which is composed of hydrogen and carbon monoxide. For this purpose, we will now move to chemistry, where we will show you how you can deposit a porous copper indium catalyst onto a copper substrate. Until now, we have seen how we can prepare the light absorbers and how we can prepare the catalyst. Now, in our case, we want to make these large-scale solar panels for fuel production. So in this case, we need to assemble these different components. Here, we will assemble the catalyst with the perovskite light absorber and with the bismuth vanadate light absorber into one single panel. Now, this is only the first step of our procedure because we will also need to make a large array of these panels. And once we have these, we can actually integrate them in a reactor that can be later used for outdoor experiments.
So before we started the collaborations, we were constrained to square centimeter systems in the lab. And thanks to this project, we could scale to a square meter and really test them in the outside real-world environment. So we think that's a very important step to test the feasibility and move forward with this technology. There are many applications. So today we are used to solar panels that make electricity. With these solar panels, we could in principle produce, for example, hydrogen that can be used for a hydrogen economy. We can use them at land, we can use them at sea for heavy transport, for aviation and many other possibilities.
So we still need to keep working on efficiency of these materials. We need to work on the absorbers to make more efficient light harvesting. We need to make different fuels as well, because there's a diverse range of fuels that we could make. There's also lots of understanding we still need to do about outdoor stability tests and understanding where losses are and where instabilities come in. So we thank our funders for making this scale-up activity in particular work. So we thank the Henry Royce Institute, the Maxwell Centre here in Cambridge, the Yusuf Hamid Department of Chemistry, the Department of Chemical Engineering and Biotechnology and School of Technology, and CAM-IES for the funding.
Right. So if I were to summarize what we have done in this project, we've created artificial leaves that make chemical fuel. And it's quite far from the actual, application in the real world. But I wanted to pull your attention to a couple of things in here. One of them is that this is a team effort. There are no barriers. If there are any barriers, we're trying to remove them. There are people from physics, chemistry, chemical engineering coming together under the same roof, or actually outside of it, because they've climbed onto our roof to do the sunlight test. And it is actually taking a lot of funding and a lot of time as well. So there are a lot of things that we need to still optimize in our research process, but it's hugely, hugely rewarding that you can do something like this just in Cambridge. We don't need to bring anybody else from the outside in this particular situation. Moving on, now for something completely different, since Multi Python is also from Cambridge. Infection diagnosis. This is still something that COVID has demonstrated how important it is, but we take for granted that in case of COVID, we knew what the pathogen was. So we just needed to say, with the lateral flow test, is it there, is it not there? With many other infections, that's not the case. The diagnosis process we take for granted, but it's far too slow. So you take a sample in any sort of form, it could be saliva or urine sample or blood or whatever, but then it's collected and it's sent off somewhere to a central lab that costs multi-million pounds with skilled technicians that take years to train and also cost quite a lot of money to run those labs. And it takes quite a lot of time before the result comes back to your GP to be able to give you a particular treatment for it, if it was, say, a urinary tract infection. So typical diagnosis takes you something like 2 days from a PCR test from COVID to maybe a week if you cannot schedule your appointment. And at the same point, we are actually using very broad spectrum antibiotics because you want to give patients some relief already, even before you don't know exactly what it is that you're fighting. Now, wouldn't it be nice if you could do a microbial infection diagnosis in 5 minutes? And I can tell you we can do that. We are doing it right now in the Maxwell Centre, in the basement lab, which previously hosted the artificial leaves. So what is important to realize is that for a proper microbial test to be efficient, you need to be able to scan for a variety of different pathogens and do it quickly and do it precisely. The team of RapidX Bio have come together as a doctor, medical doctor, engineer, and a physicist. And they harness the power of laser light and nanotechnology in order to be able to process samples, untreated samples. You can take a sample, stick it into the machine, and you get a result in under 5 minutes. By the way, there seems to be a trend with this 5-minute things. The video was about 5 minutes. This is 5 minutes. I'll come back to something else 5 minutes in a minute. And it is a tabletop 3D printed box like this. It's not very big. They've actually, I've lied to you, they've actually are currently in India testing it in the field because you can put it in your suitcase and you can take it with you to a different country. And if you're my age or older, you'll remember it took quite some time to get your photos developed. 30 minutes was a very good gold standard. And these days, imagine this, if you went with a urinary tract infection to your GP and gave them the sample, and by the time you packed up to go, you had a result and you had specific drug to treat this particular pathogen that you have. That would be nice, wouldn't it? Do you have a question?
Just a practical question. How is this different from the very malign Theranos technology? The Theranos claim the same thing, obviously.
One exists and one doesn't.
And the other thing is this is perfectly affordable. I'm not going to quote the number, but it's significantly a couple of zeros less than other technologies that we've seen so far. So if you're interested in the details, there is RapidX Bio is the website to visit and maybe catch up with the guys. Right. Now for something entirely different yet again. Can we transform how our batteries work using very accessible light technologies? To date, all the characterization of battery materials happened on the electric basis, as you would expect. But isn't it easier to look at something and see if it works or it doesn't? So, this arose through a meeting of entrepreneurial minds that happened to collocate part of their groups at the Maxwell Centre. Meet Akshay and Dame Claire. They are eminent scientists in their fields, both in Cambridge. One is a physicist, one is a chemist. They share a common interest in energy materials, so slightly different angles though. So Akshay's work is relevant to photovoltaics. Claire Gray was working for many years on battery materials. And they have many other things in common, but another one is that they are also co-founders and scientific leads in a startup company. More than one, but these are the first for them. So Cambridge Photon Technology is developing a multiplying layer that goes on top of traditional solar cells, and it makes sure that all of the photons that have too much energy to be absorbed to be turned into the electron are first turned into 2 photons. So it effectively gives you a 2-for-1 promotion on your electrons coming out from a solar panel. Now, Nyobolt has been in the news recently because they've demonstrated charging of an electric car in just over 5 minutes. So here is the same number for you. And I'm showing you this because currently, apart from research groups of Akshay and Dame Claire, we are also having a third lab in the Maxwell Centre, which is dedicated to their joint startup, which is called Illumion. Now, Illumion is another one of those box things, material looking like this. It's slightly bigger, it's about this big. And if you were to look into the labs where original research into mechanisms of materials for batteries, degradation, how they work, when they don't work, why they do not work, you will see nuclear magnetic resonance machines like this. This is where career of Claire has took off, and she is the absolute world leader. So she understands what can go wrong in a battery material. Akshay, on the other hand, is a laser physicist, so his labs are looking at very fast processes in molecular materials. Put the two together, the knowledge of how we understand the material should or shouldn't behave, and you can have a box like this. This is called Illumion 1, that can actually take battery. You can use this battery inside of the box, so you can see how it behaves in real life. And I mean it, you can see it, because this is charge photometry. You look at it with accessible light. You can actually see how charges move through the battery material. It's hugely exciting. They are on their journey a little bit earlier than some other ones. But as you get people at the contrast of research and commercial reality, they catch a bug. I've mentioned we have an Impulse program for tech entrepreneur that is very successful. We have been working with them for a while. I wanted to add what's special about our program and why is it effectively another experiment, is that this is a program that is entirely led and taught by practicing successful entrepreneurs. So this is not university taught program. We have people who have managed to do things like, I don't know, found ARM out of Acorn computers, who come in and give their time to help our budding entrepreneurs go forward. And they're quite successful. They are visible in the local ecosystem in here as well. We also work with industry and NHS and national institutions such as Royce and so on and so forth. I will not go into any of this detail because it's going away from our topic about blue skies research and so on. The point I'm trying to make is that you need a possibility to bring people who would normally don't talk to each other. And then interesting things happen. And one story I wanted to share with you actually is led out of the institutional connection with what started as a sports team and ended up as a technology development company. How many people here know who Ian Percy is? I feel better now. So Ian came to Maxwell Centre several years ago for a coffee. I got introduced to him by somebody from engineering department. And Ian was interested in how interdisciplinary research in material science, modeling, engineering can help them gain an edge in sailing races. When we had this conversation, I thought, okay, this is interesting. We should have a further conversation. We should see what we can do together. What turned out to be the case, as my team aptly pointed out to me, Ian Percy, OBE, is a double Olympic and multiple world champion in sailing. He also happens to lead, at that point, a Swedish America's Cup team, Artemis Racing. So they came in to get an edge on their competition, help from university to sail faster. They set up at the Maxwell Centre, started talking to a lot of people, and what happened was slightly unexpected. Out of Artemis Racing came Artemis Technologies, a startup that looks at how do you harness all of the new knowledge to sail faster, better, further perhaps. Unfortunately, Cambridge has one flow that I so far discovered. That flow is very important for these guys. We are very far from the sea. So after a few years of coexistence in our centre, they decided they need to go closer to the sea. They are currently based in Belfast. And what they're currently working on, so you can see there is a flying racing boat in here. And that is a picture of a prototype flying, fully electric, zero emissions people transporter. It's a ferry. So they're working on future of maritime transport that is fully decarbonized. And that's one of the biggest problems that we don't quite know how to crack yet. Think about fishing without emissions, think about people transport, maybe also goods transport in the longer term. So in the end, all of this together, we realized we have a network of people that talk to each other. And we have a mission to go out and do something that matters. For the university, one of the things that matters is looking forward into the sustainability. We had, as a university, committed an independent report from Nigel Topping. There are problems on one hand that we just go and solve because we think they're important problems, we know where we're going. There are other types of problems, and I think hydrogen economy is one of them, where it's still not exactly clear where we should be going, right? So we thought, okay, Nigel Topping report said to us, well, actually, university should work on how to get hydrogen out there in the society. That will get a lot of people together, and it will help people make tangible decisions to make it happen in the real world. Now, so we thought, okay, let's explore this further. Let's think about how this works on the scale of east of Anglia. This is not a typical place for hydrogen. We do not have heavy industry. We are actually just looking at agricultural land. There's lots of maritime transport perhaps, but it's not where you would think about hydrogen naturally. On the other hand, and thanks to Michael Liebrecht and associates, there is also people thinking about what is feasible, what is going to be achievable. The one thing out of all of this is clear to me is that hydrogen is treated as a solution to a lot of things, but we will not be able to solve all of those things together with hydrogen. So which of those should we concentrate on? That's where it gets interesting. Because if you look at what people think about hydrogen economy in the UK or in the context of east of England, there is no consensus. Those two pictures over here, that one is taken from previous government's hydrogen strategy. And east of England, which is over here, has only one potential project they would consider at that point worth pushing. Now, if you go and talk to the local industries and people who actually operate in here, they see significantly more. But at the same time, back of my mind, I'm thinking back to the Swiss Army knife. How many of this is actually going to happen? So, because we're sitting in network, we can connect people. What we can do also is we can convene people to have an honest conversation about it. And that's what we did last summer. If you're interested in this particular topic, we will be putting out a report which comes out of a conversation with government, industry, academics, and also policymakers. So things are moving forward. We have started a partnership recently with a big company called SAS Institute. SAS Institute is one of those very big companies that you probably never heard about, but they are also very ubiquitous. They work with a lot of healthcare companies. In fact, I think every single Fortune 500 healthcare company works with them. And in our case, what we wanted to do is take projects that look at the healthcare innovation. So they are developing a particular new device or maybe new material where the expertise is not necessarily in the data analytics. So here is our proof of concept. In other part of the university, Professor Gavin Pettigrew has been looking at the problem of kidney transplantation. Now, I'm a physicist, I could try to paraphrase, but I'll instead try to show you a 2-minute summary about what's the problem and where we're going with it.
Transplantation for many people with kidney failure is the best option. The demand for transplantation has increased and we struggle to find enough organs.
There was some bottlenecks to that service, and staffing is the one really that's everywhere in the NHS.
In the UK, there's about 30 individuals who can make a call on a kidney biopsy.
As clinicians, we're already up in the middle of the night making that decision. You can't run a service like that. So that's the first driver to thinking about where automation can help.
The process by which the pathologist actually assesses that kidney they were considering revolved around the ability to have images of that biopsy. And once we had that bank of images, we then thought, well, why can't we replicate the whole process and use an artificial intelligence approach to try and replicate what we do with the human pathologist?
Using a computer to do that analysis opens up a lot of avenues in terms of accuracy, reliability, efficiency.
Partnering with us, we believe, will help us to accelerate the process of transitioning from idea to implementation in the clinic.
Right from the very onset, it's been very clear that working with SAS, they have a desire to try and make things better through their processes and provide better healthcare.
It's not about writing an interesting research paper. It's about if we can get this to the clinic, if we can help clinicians make better decisions, then we've done a good job.
You perform transplants because a successful transplant transforms the life of that recipient.
You give people again that freedom to just be a human being again.
It's just phenomenal. Getting the call and getting this double kidney has saved my life.
So I guess you'll be relieved. This is last of my series of examples. I just wanted to show you one on the data side as well, because I do believe there's a lot of future potential in that. Since we're here, and since it's the Alumni Festival, and I happen to have a PhD, which is a Doctor of Philosophy, although it's in physics, I will be philosophical for a few minutes and stop this whirlwind tour with a couple of points. First of all, academia is subject to a number of measurements. There is research excellence frameworks, knowledge exchange frameworks. There is, of course, a good reason for it. We need to be accountable with the taxpayers' money that gets invested into this. But on the other hand, what gets measured gets done. And the flip argument I wanted to challenge you with a little bit today is this. None of the projects and ideas I've shown you have been predicted from the beginning. So it's kind of difficult to do this in inverse. There is a catch-22 in play, because if we optimize for what we will be measured on, then it will be done. But is this the best thing that Cambridge can do? And I truly and firmly believe that we are neither just limited by what gets measured, but also blue skies is the limit. Another point I wanted to make, and this is the quote from one of my favorite physicists, Niels Bohr, or at least attributed to him. It's also attributed to a famous philosopher and baseball player, Yogi Berra, and I can sign it myself as well, is that it's very difficult to make predictions, especially about the future. So it's the people, the journey, the number of coffee cups you can take in order to get it into the right order and actually make sure that there is a destination. And so what I've learned over the few years in the Maxwell Centre, there are some ingredients that help you get there, regardless of whether you need to pivot, regardless of whether you need to get other people on board. And one is the team. I mentioned the word partnership before, but I think it really flies when the partnerships become a team. So we're no longer talking about us versus them. We're not talking about, oh, you're a physicist, you're a clinician, you are an industry person. A team is something more than that. It's actually a common entity with a common goal. Next thing that is required is leadership, starting from thought leadership to being able to stand up and actually say, well, guess what, guys, we're not going very well with this particular thing. We need to have a diagnostic test that goes much faster than what we can currently do. Whatever it may be, that takes guts, and I think Cambridge is yet another place where you can stand up and do that because you're among other people who have demonstrated that it's actually okay to do that, and you can achieve amazing things. Next thing, however, the word doesn't usually show up in Cambridge very much. It's almost something that people steer away from. But I would like to put it back on our thinking agenda, and that is, if we are going into any game, we need to understand the rules. We need to understand if we can rewrite those rules and what is the best way we can play our game to actually win. And for that, of course, you need to know what the win means. Here goes our challenges. And as such, if you put it all together, hopefully, we deliver impact. We might not know on the day one exactly where this impact will be. It could be your astrophysics galaxy search that ends up in the mammogram analysis. It could be something else. But if you play the game, you can hope that something nice will happen. I hope I've demonstrated enough of examples that we will hopefully build much more on in the future years. So, if you forget everything I said up to this moment, I want you to take one learning about the Maxwell Centre from this talk, and that's this. Think about a pinball machine, right? So, if we are, as Maxwell Centre, part of the ecosystem that exists in the university and outside of it, I would think we are those white flaps at the bottom of it. It's our role to understand what else is out there, who else any particular project, a ball traveling through this pinball machine, needs to get to, where they will best get most momentum, which off-ramps are they supposed to be aiming for. And occasionally, if it doesn't go right, that's okay, it'll come back. We'll re-inject most of them. We cannot catch everybody, but most of them will go traveling, maybe on another journey. So that's that. And coffee fuels conversations. So please join us for a coffee. We all have a stake in society of 2051. Let's talk. And I wanted to acknowledge my team who works in the Maxwell Centre on our industrial knowledge exchange and partnerships. Thank you for your attention. Do we have any questions? Yep.
I wondered if you had the slide with your vision on for the Maxwell Centre. It can maybe pop back to that. So
Yeah.
I work in innovation, and one of the things we're questing for at the moment is a vision. And
Yes.
I think you voiced that you were involved in creating that vision.
Yes.
And I just wondered if you could talk about how you came to it, what you considered in or out. I was interested to hear
Yes,
more
very
there.
much, no problem. Glad you asked, actually. It was very an interesting process. And first of all, there's a lot of things, this one, yes? There's a lot of things going on in Cambridge, and there is a many flowers bloom approach. So if you have a good idea, you're usually allowed to run with it. That's good, but if you're in a center like Maxwell Centre, you want to know that you're heading for a space that is not already occupied, so you're not going to be duplicating, you're going to go for something that nobody else is thinking about. And very simple approach, the sort of gauge that I took to start with, is first I wanted to know that we have topics that we can engage with that have enough of bandwidth of expertise and capacity to get involved with some new experiments, new collaborations, new partnerships. So the first thing is the bandwidth. The second is the headroom. And we have a lot of headroom. If you look at the batteries, if you look at the computing machinery, we have data centers that are very functional, but they also heat the environment around them quite a lot. So there's this zero waste came into mind. How can we optimize what we do and also optimize what we don't want to do? So the bandwidth comes from a lot of coffees of conversations going in the Maxwell, somewhere else where we can go and talk to people and bring the right people to the table, talking to industry as well about where they think that direction of travel should be, where they are interested to come, because it's not only about us wanting to go somewhere. So yeah, iterative process, pivoting a few times. I will maybe pick up over coffee with you about the hydrogen economy, because it was also a little bit finding out where are we going to land with that particular conversation. Yeah.
Always wanted to build on that. So I work in impact investing. So one of the key things is about decision making, about uncertain outcomes and impact, and the relative allocation essentially of resources to them. So
Yes.
you talked about some of the criteria that you've learnt about given that huge uncertainty. How do you decide who you take on and what projects you work on, and how do you decide when to stop?
Yes. So how do we decide to where to go is we usually have many more projects than we can potentially accommodate. So we want to know what the people are thinking from their perspective that they will gain from coming and working with us, and we know what we think we will gain from working with them, and we ask them to articulate how their presence precisely in the Maxwell Centre will help all of those aims rather than being somewhere else. So that's the first pass. How we decide when to stop. So for example, with the demo lab, it's quite easy because we sort of agree upfront what is the next milestone that we want to get to. If it doesn't work, that's fine, it can go away and do something else, or somebody else can come and help with it. And with the decision making, there are really nice methodologies for the decision making, and the important thing I would say is not to get too hung up on having perfect information, because you'll never have that and you'll wait forever. So just get to the point where you're secure that you've explored all of the options and you have a good logic about why you're going for that particular one. Thank you.
Thank you. Great presentation. I don't know whether it was deliberate or not, but I just saw AI being mentioned once in a video, and rightly or wrongly is considered a foundation of innovation. So where is AI fundamental, or is it just a tool, or is it everything in terms of innovation? How do you view AI?
Well, AI is not quite yet where, in my personal opinion, where it will possibly be able to go, but it is a tool. At the same time, we need to be a little bit careful about how we use it, because it's only going, any algorithm is only going to be as good as the data you feed into this. So we need to be careful and progress slowly with AI when it comes to critical decision making. But having said that, AI has already a role to play and can do many things immediately. And one of those things is it can actually help us compress the timescales. So AI is, I think, perfectly capable as of today to take away some of the painful things that researchers have to do, the mundane stuff, because that's what AI is usually good at. So if you take away all the time that is not wasted, but necessary, put aside to doing things that are not in the lab, can we progress faster? And I think we can. And that goes beyond AI, it goes to end-to-end integration of your data streams. So all the knowledge you already have, you can plug in from one end, then follow the data through your process, through your research discovery, through planning your supply chain for your manufacturing, where you get it through, and then kind of what you've learned goes back in. And by the way, I've just described how Moderna's model works, so to acknowledge that. Yeah, I think what I said before, and I stay by it, I cannot imagine a world of 2051 without data and algorithms. AI, of course, is a part of it.
Sorry, hi. I run a small business in skincare, and I guess one of the central pillars you mentioned talking about for the Maxwell Centre is collaboration and getting people together. Do you do much with small businesses in industry, or is it mainly sort of the big guys?
It's actually everything in any size and any shape and almost any geography. We are looking for partnerships where we have, back to the question we had before about sorry, it was your question, about how do you decide? Decision making involves where is the most value added. So if you already have all of the capacities and you don't need us, then that's not a good partnership. If you have a really good problem though, and very hard one especially, that's where I think many of academics get excited, because they really want to dig into something that is not trivial. And then actually partnerships becomes quite natural. You can work on a problem that involves a big scale company as well as a startup, as well as SME. I have a project we've done 2 years ago in this particular category that I'm not going to explain right now, but there is no, oh, you're too small or too big or too far. You were next.
Sorry, I think you probably alluded to this all the way through, but I was just curious, do you have any sense of what patterns of innovation, especially around the early stage of the start of an idea, are actually that you guys have found most successful?
Don't think I will risk to make a very solid statement on it. Coming back to, it's very difficult to make predictions, particularly about the future. But I think where I see the innovation progressing fastest is coming back to your point about people being good at decision making and grounding what they do in reality rather than what they wish to be true. So if you actually get to the next milestone, you know where you're going, and then if it doesn't work, that's okay. You can hand it over, you can think of a different solution. Just don't flog the dead horse. I think that's the thing that I would avoid. So if you look at sometimes you get so married to your own idea or your research, you know, that it's very difficult to do that. But it is easier if you work with people who come at the problem from different directions, because if you're open-minded enough, other people will say, well, by the way, this doesn't quite work possibly because of this. And if you're an honest scientist, you will look objectively at the matter and say, well, okay, you're right. And you're not going to try to create solutions in search of problems. So that's why I think that one of the ingredients of I think some of the innovations that we are going ahead with and are successful is that you not only see groundbreaking research with leading experts that can take pretty much as good a guess as anybody else in the world, but you also have them in front of companies and industry, and they will come and say, okay, well, that might be the best way to do this, but actually it will not work in our environment because X, Y, Z. And putting those two together is like a lightning strike. You have negative and positive potential between the ground and sky. Technology pull, technology push comes together, off we go. I know it's a little bit fluffy, but you know, that's what it is.
Thank you for the talk. And then I have one question, especially when we talk about innovations or discoveries in a situation like the academia-industrial partnership. How, when it comes to patents or like, you know, profit splitting, how does that work?
Oh, that's down to the contract. Quite often, I think we are in a really good situation in the Maxwell Centre because we are not operating at the level typically as a normal technology transfer office would. So we're not waiting until we've worked on something until the point we know we have a patent. It's pre-competitive. Quite a lot of our problems are hard. Nobody knows how to solve them. Big companies, some of the biggest competitors might be willing to come together to work on it because neither of them knows how to go into that field and how to solve the problem they have. So I think it's again one of those tools things. Sometimes it helps. Sometimes it will be allowing you to take an innovation forward, and I am very glad that the university has a very sane approach to intellectual property and taking it forward. In some cases, I come back to sort of the origins where IP came from, right? In early days in America, it was a toolkit to stop somebody else getting somewhere faster than you. Now, if you take that in the context of climate change, is that what we really want to do? So you have to just take every particular thing with a logic behind it. Sometimes it's going to really help you because nobody's going to invest until they know that investment is protected. But on the other hand, maybe it's not always the right toolkit. Thank you. Final question, maybe.
I was just following on from that. Very, very interesting presentation. I went to a demo day done by Undaunted, if you know them. They're Grantham Institute and Imperial College. It's their accelerator that they've got. And they provide commercialization support for scaling up these ideas, which goes beyond funding. It's also go-to-market, marketing, all the other features and aspects you need to scale up a business. I was curious about.
Yes, we do. I'm going to probably fuffle too much with my slides here to find the right one, but basically the one I had about Impulse program, we provide them with enough of knowledge so they can get started in this space. We provide them with the network. So community of the Impulse program is 100+ successful entrepreneurs, patent lawyers, financiers, VCs, anybody that can come and be useful. And then the university also has recently launched a program called The Founders, where they pick a cohort of maybe about 10 companies, work with them very intensely on that particular business model, on where they need to move forward. And so we do that in Cambridge. It's not an end-to-end thing, but maybe it's an alternative that is worth considering, because not every, going back to the pinball machine, not every project travels the same way. Thank you very much.